Welcome. Today we're going to talk about recurrent neural networks. So you might recall last lecture we talked about convolutional neural networks. Convolutional neural networks had the important property that we used that the inputs, often images, typically have some sort of spatial structure. And this type of spatial structure was very nice and convenient in the sense that by exploiting that idea that prior we had over what our data looks like, that sort of spatial structure let us use a certain type of weight sharing. Well, recurrent neural networks are somewhat similar in the sense that they're also going to let us do some weight sharing. The thing is, instead of sharing weights spatially, we're going to share weights over time. And so the important concept that we're going to discuss are sequence models. And sequence models. A sequence model, suppose we have a sequence of points where each one is dependent on other points in the sequence. This is going to be the type of setting where we look at, and somehow the kind of goal is to be able to predict information or combine information about multiple points in the sequence to do machine learning. So let's talk about a couple of examples. There's two examples. One common example is stock prices. So for example, you can suppose you have stock prices x1 through xn at various different times. So maybe on day 1 the stock is $1, day 2 it's $1.15, day 3 it's $2, day 4 it's $1.25, and so on. So the idea is that we have these prices, and maybe one goal that you'd like to have is you'd like to predict stock prices based on previous stock prices. So the type of model you would have here is you want to predict x hat t, which is drawn from a distribution which models the probability of xt given x1 through xt minus 1. So the idea here is essentially what can the price or the stock price at day t depend on? Well, it can just depend on the prices in the days before. And it can't depend on the days in the future, of course, or it can in some weird sort of causality type of way, but we're not going to get into that. The point is, you do a prediction based on the price in the past, and that's what you get. Now, what this probability is not exactly clear, and that's where our machine learning models are going to come in. They're going to allow us to predict what a price will be based on the previous prices. So that's one example. Let's see another example before we get more into the details. We just want to see some applications first, like what type of places these might be useful. And the most common place where sequence models come up is almost certainly language models. And language models, they work kind of similarly, though a little bit in disguise. So yeah, basically all the recurrent neural networks, or not all the recurrent neural networks, but many of the recurrent networks or sequence models you'll see, they operate on language models and try to do language modeling and all sorts of different tasks, generative language or prediction on language and stuff like that. But there's sort of one basic underlying question whenever you're doing a language task. One of the most fundamental questions is the following. Given a phrase, what is its probability? So this might seem a bit odd to you. How do you predict the probability of a phrase? Well, we generally assume that the common way to model language is to assume that data or phrases are drawn from some distribution. For example, let's suppose we want to predict, we could potentially have a probability that the cat is black. There's a probability someone could speak this phrase or write this phrase, and it's a non-zero probability, so a relatively reasonable sentence to write. So on the other hand, something totally crazy, for example, if the probability of like is black cat, this is going to be much less than the other phrase and probably pretty close to 0. But the point is, it's a reasonable question to ask, what is the probability of a single phrase here, like this, where the distribution is over the set of all possible phrases that humans would say, or natural language. So the thing about this probability is we can sort of break it down into sort of its components, where we have the probability of seeing the word the, and then sequentially you can ask what times the probability of seeing cat given the, times the probability of seeing is given the cat, times the probability of black given the cat is. So you can always, I didn't do anything special about this special to language models. I just basically broke it up using elementary facts about probability. And now you can see when I write it like this, that this actually kind of resembles the previous type of predicting stock prices. So a very common task that you will do in language models is you'll want to predict the next word. This is very natural. For example, when you type in something on your phone, it'll try to predict what the next word you want to type is. And indeed, that's exactly using like probability distributions over what people type. And in particular, when you type things into your phone, Google also learns, or Apple or whatever type of phone you have, it also learns what your specific distribution of words is. So yeah, this probability distribution might be specific to individuals. But okay, so again, this is just a simple prediction style task, next word prediction. And it's something like this. It's basically asking, you want to predict x hat t, which is going to be a sample from a distribution x sub t given x sub 1 through x sub t minus 1. So this is the exact same thing we had back here. This time, though, we had a different meaning for all of these different things. This is going to be the next word. And these are previous words. So now these are just two examples of where sequence models can come up in machine learning, and indeed, especially language models are a very common application where we use them. Now, the million-dollar question here is, how exactly do we model this distribution, and how do we learn this distribution? For example, it seems like a rather daunting task to learn the distribution of all possible English words and that people use. Well, it's not so bad once you parameterize it and just use the same type of tools that we've learned before. In particular, surprise, surprise, we're going to basically parameterize this probability distribution and make it into a neural network in the appropriate way. So let's take a step back though before we get to that. The idea is the following. We're going to keep a summary of past observations. So for example, when we're doing some sort of when we're doing this, we could always keep, when we're doing next word prediction, we could always just keep the list of all words we've seen before and see what happens. But the thing is, this would be rather difficult because of the fact that there's so many different combinations of words and it's not clear how they relate to each other. And basically we could see prefixes of a sentence that we've never seen before, so we might be conditioning on something which is a 0 probability event. The point is, if you just stored the past history of words you've seen, then this might lead to, this might not be possible to compute or even approximate what this this probability is, because you're conditioning on something you've never seen before. So instead, what we're going to do is we're just going to represent the history using a vector. So summary will be, say, ht, which is a vector. I'm not going to specify dimensionality of this because it could vary depending on how big you want your hidden state to be, but I'll just write down that this is a vector. Okay, so if you have this summary, then all you have to do is replace this history using one of those. So for example, in this example, it would be something like then x hat t, which is distributed as probability of x sub probability of this, given conditioned on the realization of the summary vector, or sometimes the hidden vector, the hidden state vector, something like that. So if we do something like this, then it becomes more tractable, and you'll see how basically we're going to do similar types of things we did before very briefly. But okay, so the question is, what exactly is ht? This is a function of x1 through, say, x sub, let's say sub t, basically all the previous observations. I guess we'll just do a little bit of a re-indexing here, so that it'll basically use up everything through xt, and then we're just going to update it over time. Now, just to give you an example of what I mean, the idea is we won't always compute ht as a function of all the previous inputs we've seen, but we'll compute what we'll have at each time step is we'll have a previous history and the current input, and we'll update our summary based on the previous summary as well as the current input. So let me just write some stuff here and we'll see. So what we do is, first of all, our first summary would be some function g of, first thing will appear in it is x1, so the first input, and the previous history will also go in it. So we don't have a previous history, so we'll just have some sort of, I don't know, you can pretend the zero vector is here, some initialization or something. Let's just put, say, the zero vector in here. So the idea is at the first time step, it's just going to compute some function based only on the input. And then from here, yeah, then we can do some prediction based on that. So I guess I've got a weird type of indexing here, but let me just write it like this. So our prediction next will be y1, which would be a sample from some probability distribution given x1, conditioned on h1. I guess let me write it like this, sorry. Like, I'm going to deviate a bit from what I did above. What I did above was I sort of assumed that we were trying to do specifically like predicting the sequence itself, but let's just be a little bit more abstract. In particular, let's say we're trying to predict some other value, some sort of label for the points, or labels based on the sequence. We'll see some applications of where these could be different things in the future, a bit later in this lecture, but the main idea is that we're going to predict some value at each time. And this may not exactly be x1. If this seems a little bit unfamiliar or odd to you, then you can just pretend, for example, if you just want to simulate the setting we were talking about, then you can say e.g., say y hat 1 equals x hat 2. Something like that. Well, what I'm saying is like, this is the sort of way that we would do next word prediction. That, yeah, maybe you want that, not that. Say, for example, you might want the next, so this is how you'd simulate next word prediction. In which basically at time 1, you're trying to predict the word or the input at the next time. But this is going to be a more general. Hopefully that's clear. So, okay, that's how you do the first time. You basically summarize the past history, then you also take in the current input, you make a hidden state, and then you make a prediction using that hidden state as information. Okay, that's good. That's the first time step. What we do at the next time step is going to be very similar. We just take in, now it's a little bit different because you can see that we take in, again, we take in the current input, but we also take in the past history, which this time is not just the zero vector because we actually have a history or a summary. I'll use those words interchangeably. And similarly, we can do y hat 2, probability y2 given h2, and so on. So let me try to illustrate this with a diagram to try to show you how the information is flowing and how things are flowing through this. So we can pretend these down here are the x's. And then here we have h's. And here we have the y hats. And then coming from here, we have previous things. Okay, but hopefully this makes sense. The idea is that there are going to be these elements of the sequence, which come x1, xt, and so on. It's kind of a, however, it's a variable length sequence. It could be maybe short, it could be long, it depends. But the idea is that at each time step when you feed something in, then how does the information flow? Well, this input, it goes into this hidden state. This hidden state is kind of a function of two things. You can see here, it's a function of the input as well as the previous hidden state. And then somehow, based on these things, these two, based on, I guess, the hidden state, we make some sort of prediction. So of course, this is just to illustrate how the information flows, but like the thing that we haven't talked about exactly is, you know, how does it go? What do the arrows represent? They just say that somehow we do some computation. ht is some function of ht minus 1 and x sub t, but it's not clear what function. We haven't talked about that yet, so we're going to talk about that first. So like, let me show a question mark, and then afterwards, immediately after, we're going to talk about how we define something like this. So yeah, how would we actually compute this hidden state vector? Well, let's talk about that. Well, it's very similar to what I wrote above in the sense that you saw here, we wrote that h sub t is going to be basically the function g of some function g of the previous hidden state and the current input. Well, that's exactly what we're going to do. I'm going to change it up just a tiny little bit. So I'm going to write it that h sub t is equal to some function f, which is a function of h sub t minus 1, x sub t, and importantly, theta. So, okay, so we're saying we're going to determine our next h sub t as a function of three things. Let's talk about what each of these are. So we're going to, the next hidden state is going to depend on the previous hidden state. It's going to depend on the current input. And it's going to depend on some parameter vector. Theta. Now, let me comment on this just a little bit. You'll note that this is really not so different from anything you've studied before, in the sense that it just takes in some inputs and it's going to be some function which produces an output. So it's pretty straightforward like that. And the important thing here is that note that this parameter vector, theta, is not time indexed. So while we take the previous hidden state at time t and the current input at time t, note that there's just a non-indexed parameter vector. So this is going to represent all the weights and biases in our model, and it's just one thing for all time. So we're going to reuse it for time 1, for time 2, for time 3, for all times. So this is where we mean parameter sharing, in the sense that for convolutional neural networks, you'll remember we did parameter sharing over space. That is, we knew spatial things about what a picture looks like or what an input to a CNN looks like. And based on that, we would share weights because that's sort of the right thing to do. Well, similarly, we're going to share this parameter vector over different times because we make the implicit assumption when we're dealing with a sequence model or when we're in an RNN setting that somehow the function at different times is going to be somehow similar. Or there's some sort of structure in how the sequence looks, which is sort of kind of time invariant. I'm not being totally precise here, but at least that's the idea. Somehow it doesn't have to be a totally different parameter. It doesn't have to be a totally different function at each time step t. If it did have to be a totally different function at each time step t, then it would be kind of impossible or very, very difficult. We would have to build some sort of more in-depth network models, or maybe something fully connected, which would be more fine-tuned, and that would have a lot of parameters. It would be more challenging. But it turns out in many cases we can do a lot better just by assuming that there is some sort of shared parameter vector which is not time dependent, and yeah, that lets us save parameters, a lot of parameters. So yeah, and sort of as I've alluded to, we are going to, what type of function f are we going to use? We're going to use a neural network, unsurprisingly, perhaps. Okay, so just to try to illustrate what this looks like, just the function h. So let's try to sort of delve a bit deeper. For now, we're going to kind of go back to this type of image, but maybe be a bit more specific about the details. But for now, we're going to chop off the top part. We're going to just focus on what does the neural network look like in terms of just looking at the hidden state progression. And it looks something like this. I'm going to draw it concisely at first, and then I'm going to unroll it. Yeah, for now, forget about the output, but it's going to look like something like this. So this is what a recurrent neural network, or a very simple one, which just stores the hidden states, would look like. Now, this is a concise way of writing it in the sense that you note this weird box I drew here. Well, that just means that you feed h back into itself with a time delay. So try to convince yourself and see how this might correspond to this type of equation. You can see that h is determined by feeding itself into it and by xt. So that's kind of where these two things come from. And the parameter vector theta is going to be the sort of union of u and w. So that's just going to be our parameter vector. Okay, so try to at least get some intuition as to how this corresponds to this, and I will draw out what it looks like unrolled. So unrolled because it looks more similar to what you might have seen before, what we've looked at before. And so on. So yeah, this is kind of similar to the image I drew before, except now I've been a bit more specific about these parameters. Note importantly that these parameters are shared. These u's here are the exact same u for the left and the right. So do parameter sharing similarly for these w's. And hopefully you can see how this kind of corresponds to this diagram. The one on the left is just a more concise way of writing it. But yeah, you can see x feeds into h via this u, and then it feeds into itself over time with this w in the middle. And let me be a bit more precise as to how we actually compute this. I'm just saying take some combination of these. Well, that's not exactly what it looks like, what it is. In particular, we let h sub t be equal to, there's going to be a non-linearity here, so it's going to be tanh often of wh sub t minus 1 plus u x sub t plus b, there's a bias term which I just didn't put in anywhere because it's not clear where exactly to stick it. But anyway, this is essentially how ht is calculated. And you'll notice that this is a very simple and familiar type of computation. This is exactly just a multi-layer perceptron style computation on the input. In particular, you know, when you have a neural network layer or a neuron, you just do linear combination of the inputs. Well, you do a linear combination of the h's, you do a different linear combination of the x, add on a bias, and then you apply nonlinearity. So really, this is not so, it might be a little bit more intimidating because we're like dealing with different time steps, but really it's just the same thing as we've seen before. We make little neural networks at every point, or we put neurons at every point, and then it becomes a neural network. So yeah, let's okay, that's good. Now let's see about what it looks like when we have a neural network which is meant to do, say, hidden. What do I want to say? Let's say this isn't a very useful neural network because of the fact that we don't really have anything we do with it. We just compute these hidden states and move on with our lives. But let's suppose we actually wanted to do something useful, like we wanted to do, say, next word prediction or something. What would the network look like there? Well, we have to do something with this hidden state. So let me draw it. Actually, let me just augment this previous one, actually, because it's easy enough. All right, we'll lose that W. But yeah, let's move this down. So let me just augment this diagram a little bit by writing a little bit more on it. So we'll have some output with this H, and that will be another type of thing that we do right here, and Y hat. Have some loss function L. Y feeds into this. So you can see what I've done here. There's a few things. What we do is we first compute some function of the hidden state to get some sort of output. So for example, this could just be like a final fully connected layer, something like that is the kind of idea if I want to draw an analogy to yeah, maybe a fully connected layer plus a softmax to draw an analogy to some of the MLP stuff and the CNN stuff you've seen so far. And then we get some sort of prediction. And what we do is we feed in the prediction as well as the true value to some loss function to calculate the loss, of course. So let me just expand that out here, what that looks like in this part of the diagram. So that would give us something right here. Now note when we do this unrolled version, it would be a Y hat sub t. And then we would have the loss function right here, Y sub t. And similarly, so on in time, Y hat t plus 1. So yeah, that's sort of what the network looks like. Let's see a bit about what, let me zoom out a bit. We want, how do we generate these things here? Well, like I said, we have these parameters v here, and we just do it as follows, Y hat sub t. This is equal to, say, softmax of v sub ht plus c. So again, just like I said, it's just going to be kind of a fully connected, or we just do a linear combination of the hidden state and then take a softmax, where again, v and c are the tunable parameters here, the learnable parameters. And the last thing I guess we need to specify is how do we compute this loss function? Well, it's going to be not too surprising, you just sum out things up. So in particular, suppose we have some sequence x, which is the input, and our sequence y, which is the desired output. Well, we can just compute this by summing over the y t hat, where t goes from 1 to, say, n, however long these sequences are. And notice that there's a function of sort of the network model, the network parameters as well as the x's, that's sort of implicit in this y hat t. Good. So that's just a basic example of what a simple RNN looks like. Yeah, it's really not too complicated that once you get the idea that it's sort of temporal into your head. So let's do a simple example with one, like a kind of a mock computation. just to show you kind of the idea of how this would work, because we've left it a little bit abstract, let's do a little bit more of an example with next character prediction. So let's suppose we wanted to feed in the word hello to a model, and we wanted to, at each time step, predict the next character. So we type in H, it should predict E. We type in HE, and then it should tell us L, and then it should, based on that, tell us L, and then O as the last letter. So that's kind of the idea of what we're going to do. So let me sort of write this out. So our input layer will look something like this. So the idea is that we're going to feed in the input HELL, and then O is going to be the last prediction. So let me just write these here. And you might be first wondering, how exactly do we feed in a character into a neural network? Well, what you have to do in general is find some sort of way to convert a character like this into a vector of sorts. And so the simplest way to do it is just a one-hot encoding, as it's called. So basically, the first letter, the first input is going to be 1000, because we know there's 4 things in our vocabulary here. Well, 3 here, but there's also going to be O. So similarly, 1011, 10100, we have 0010, and then 0010. Those are how we represent the inputs. It could be more complex. There's other things called word embeddings and stuff like that, and so you can have more complex vectors based on the inputs, but we're just going to keep it simple for this example. So the idea is that we're going to kind of, when training at least, it's going to look something like this. We're going to feed them in, and then we're going to get some values in the hidden state, the hidden layer. Minus 0.9, let's say I'm just making up some numbers, 0.1. And then based on that, we get some sort of output. This is going to be V, and then there's going to be some softmax. But basically, we get something that looks like this, which let's say is 0.2, 0.3, 0.1, 0.4. And so our expected output was E. Let's say our target. Our target output was E. Now, what did we actually predict with the softmax? Remember, we just take the max of the 4. Well, it looks like the max of them was the 4th space, which is O. So our prediction was incorrect with this one. So we would suffer some sort of loss based on that. I guess it would be more complicated because we would really take the cross entropy loss with the vector which places just a 1 in the E spot, which is 2. So we would take the cross entropy loss, but if we were just doing a prediction here, actually you can see we got it wrong. So that's not great, but it might be okay for better later time steps. Okay, so we did the first type of prediction, but remember, we feed this hidden state onto the next time step. So based on the history, it kind of knows what we know already is now we know the sort of this vector here will summarize what we've seen so far, which is just a single H, but somehow it has encoded that in this hidden vector using some sort of encoding which it learned. And now feeding in this other vector, well, we can combine it, and in some way it'll give us a vector that maybe looks something like this. And from that, similarly, we do another prediction, which maybe this time it'll be like 0.15, 0.15, 0.3, 0.4. And remember, this time our target is the next character again, which is an L. However, once again, it made a mistake in the sense that it got it wrong. It would have predicted O again. But yeah, we can keep doing this. Maybe this one will be 0.1, 0.3, 0.5. And then maybe it'll give us some sort of output vector that looks like this. And this one, the target is L, and this time it actually is correct. So that's good. And then maybe the last time step, it'll look something like this. I don't know. Maybe 0.1, 0.3. Again, these are kind of arbitrary numbers. There's nothing too special about this. I'm just trying to illustrate how it might look. And our target is O. And in fact, yeah, it gave that. So that's kind of how it would, how a neural network might, an RNN might look like when we're training it. You kind of feed in the inputs, they progress through it, they'll make a prediction for each time step, and you incur some loss at each time. And based on these losses, you can kind of compute gradients and compute losses. Well, we'll talk a bit more about, only a little bit more about how we actually compute gradients here. It's not too complicated if you understand back propagation already, but yeah, it's just not really the focus. But yeah, the point is that you'll basically do predictions at each time, and you'll incur some losses, and also you can see the hidden state propagates through in order to help us make future predictions. So this is how it looks like during training time. Now, during test time, it's a bit different. Like, how would you actually evaluate a sentence or do this next character prediction problem? Well, you can't just what is it, compare, maybe you don't know what the next characters are, right? You're starting with something that starts with H, and you want to predict the next character. You don't have it there already. So instead, if you were doing something like this actually in practice, at test time, what you would do is you would feed the outputs into the next input. So for example, from here, you'd have some sort of output, and then you'd go and feed that, and that would become the input for the next thing. And similarly, it would have a next character prediction, and it would go and be the next input, and similarly, so on like this. You can see how these kinds of models are perhaps somewhat differently used sometimes when you are either doing things at training time versus test time. But hopefully that makes clear what a sort of RNN looks like. Now, this is just a simple and common setting of how we might use RNNs, but let's talk about other sequence problems. Like, this isn't the only type of thing. This is basically all we've talked about so far, where you have something and you want to predict the next thing and you want to predict the next thing. But there's many other places where sequence models come up, and where RNNs can be effective and useful. So examples of other sequence problems. So yeah, this is a very flexible framework in the sense that it allows us to have a variable length input and output. And yeah, sometimes we actually have fixed. Like, let me show you one example. So one example of way we can use it is many to one. In the sense that what we can do is have a long sequence and only have one point as output. So this could be like, let me just draw it without putting names on these, but you can picture them x1, x2, x3. So maybe we do something like this. We have some sequence which we feed into it. And then when the sequence ends, then we just do one thing out. And when could this be useful? Well, a common application of this sort of thing is sentiment classification, or just any sort of classification problems on text, really. In the sense that maybe you feed in some sentence and you want to predict something about that sentence. Well, an RNN is a very natural way to do it. You just feed in the sentence one by one, and it'll store some hidden state. It'll basically figure out things about what you've written so far. And when you finally get to the final hidden state, then you can just do some prediction on it, just as we've done before. So just to give you an example of what sentiment classification is, it could be like this. Movie is great. Well, this would be a positive sentiment. And also you could say, I hated this movie. Something like that would be a negative sentiment. So you can maybe picture how this would go into the neural net, the RNN. You just feed it in, say word by word, and then it would spit out, based on the final hidden state, you just do a neural network computation and it would tell you plus or minus 1, which is a prediction of the state, of the sentiment. Okay, so that's one way. Well, you can also do the opposite way, one-to-many, where you just feed in one thing and maybe it's supposed to output some sort of sequence. So for example, you can think of this as being any sort of text generation task where you want to generate some text, for example. I wrote some of these as circles, some of these as squares. Don't read too much into that. It's just my poor artwork. But okay, so this is what you might picture as a one-to-many, where you just feed in one object, whatever it is, and then it'll spit out maybe many outputs. And for example, example is image captioning. For example, let's say here's a picture and you draw something like this. And maybe this is supposed to be a cat of some sort. And you feed this into the neural network. There's nothing saying that you have to make it be a string or something. This could be just the image you pass in. Maybe there's some sort of convolutional network that goes into this. But the point is that you just feed in some sort of image and maybe it'll give you some caption. Something like that. So text generation is a frequent case where you'll have a many length output. In particular, we've talked about many to one, one to many, and a common, perhaps maybe even the most common one, is many to many. This is, for example, you already saw one of these when we talked about next character prediction or next word prediction. Basically the examples we talked about before, but yeah, let's talk about another example which has a slightly different setup in terms of what it'll look like. I mean, you can really put this however you want, but the picture I'm going to draw here, let's have something like this, where it'll take in some input, and then it'll start producing output, something like this. So yeah, you can see it takes some input and some variable length output. And yeah, a common application for this type of thing would be machine translation, where, for example, you feed in some sentence like the cat is black, and the output, so you feed that in maybe here, and the output would be something like le chat est noir, something like that. So you can see how this takes in a sequence and it gives you out a sequence. Yeah, I'll note that this one in particular is relatively easy because it's a very simple translation. You might be thinking, okay, why did you even have to wait to see the whole sentence? Because it's not even really necessary. You could just translate them one to one. They're in the same order. The translates to le, cat translates to chat, is translates to a, and black translates to noir. But sometimes it can be, depending on the language, things could be a little bit different. For example, there could be variable length, and you might have to see more of the sentence to be able to translate it. For example, I'm not going to try writing this, I can't write it, but for example, these characters here in Chinese, doibuqi, translate to sorry. So you can see here that you kind of need to see, I'll claim at least, maybe you don't know, but you need to see all of these characters before you really know it means sorry. And also, you can see that it's a variable length. The input and outputs are different lengths. The input was 3 characters, whereas the output was just 1 word. So yeah, hopefully this gives you an idea of how flexible these RNN architectures can be used. They can be used for any sort of tasks where you have sequences, either as the input, as the output, or both. Okay, let's talk a little bit more, hopefully get the general gist of what we're looking at when we're doing RNNs. Let's talk about one more detail about the architecture and how we set it up. And I'll write this as sequential versus parallel. So let me bring in essentially just a copy of whatever I've shown you before. This is just a figure from the book, the Deep Learning book. It's pretty much the same as what I drew above, except with a few small notation differences, nothing too big a deal. But yeah, you can see that this is this is essentially what I had before. And what is the downside of this type of computation? Well, the downside of this type of computation, when we do computations on this, is that it forms rather long chains. What do I mean by that? Well, I'm not going to get too much into how you do backpropagation here, but the idea is that, remember when we're doing backpropagation, typically you have your predictions, you kind of have to compute the gradient with respect to all the parameters in the model, and you kind of follow things backwards. So from this loss L, you'll have to do a computation, both in terms of gradients as well as the computation itself in terms of computing this loss. There'll be a very long chain in the sense that you have to go from this to this to this, and here you have to go back in time and back in time. So essentially, if you want to do a prediction and compute some loss for the tth time, you have to include computations involving all previous times as well, because it's a very long chain, which can have a few negative repercussions. In particular, one thing is just it's a very long computation. If you have a long sequence, then it might take a while before you get to the end of it, which incurs some latency. And also, this might have difficulties during optimization just because you're going through so many layers in your computation. And as we'll talk about in a bit, this could lead to vanishing or exploding gradients. So yeah, this is something that's a bit weird and a bit annoying. There are some issues when optimizing RNNs, but one way of getting around this is by, instead of looking at this network in particular, we actually look at a slightly different style of network, and it looks something like this, which looks almost exactly the same. So let's put them side by side. So just to keep in mind, this one is what we've talked about so far on the left, and this one is the new one on the right. So this one can be seen as more sequential, whereas this one is more parallel. And let's compare the differences. It might not be immediately apparent why this is a more parallel model, but we'll get to that. So you can see the only difference is where we connect to the next hidden state. So the way we've done it so far is this right here. We connect the old hidden state to the new hidden state. But what we might do instead is, instead of doing that, what we can do is compute, say, v times the hidden state and then put it through a nonlinear activation, and then we get to this O right here. So basically some sort of other vector, which may be, some sort of transformation of it in the typical way. You know, the typical linear transformation, then nonlinear activation. So this seems like a fairly minor difference. We're just, say, connecting a different stage. We're just doing this instead of this. But it actually makes a difference in a few different ways. The first way it makes a difference is this type of model is actually more powerful. Let me just trust me when I say that this is more powerful, in the sense that it can be formalized into showing that this is actually Turing complete in terms of being able to compute many, many different functions. It can essentially compute any function you want, whereas this is not Turing complete. However, this has other advantages. This is parallelizable. And it might not be immediately obvious as to why that is. In particular, as I've written it, or as I've stolen it from this book, it is not actually parallelizable in this way, in the sense that it just goes through this long chain as we did before. However, there is a neat trick known as teacher forcing, which will essentially break up these long chains, and that'll get rid of these long dependencies that we had, which both have downsides in terms of inference time, like training time, as well as gradient computations. And in fact, it'll allow you to basically compute this in parallel for each different layer here. I'm not sure if layer is the right way to say it, but like layer in time. Each of these can be computed independently, whereas as we have it right now, they have to be sort of computed together. So we can parallelize by doing something known as teacher forcing. So let me bring in yet another diagram, which is here. So you can see, actually, this is how we are going to use the one on the left, or on the one on the right. So let me move some of this around. So yeah, this is kind of a caricature of what we're going to do in terms of breaking up these chains. So this is, I'll just label this as teacher forcing. And just pay attention to the side on the left here first. So what we're doing here is in this image, when we're doing these connections in this network, we connect the hidden state to the of one time to the output of the previous time's hidden state. So it's kind of like, yeah, we're connecting this O here, this output, to the next hidden state. But what is O supposed to mimic? What's it supposed to represent? Well, what it's supposed to represent is this Y here. Like ideally, O would be equal to Y. And if O is equal to Y, then we would be able to use O and Y interchangeably. So in reality, unless we have a very perfect model, O is not going to be equal to Y. But that's kind of okay for the training phase. So the idea is that rather than incurring these long dependency chains, which go zigzag like this over time, what instead we can do is, when we're doing training time, instead of feeding O from one time step into the H at the next time step, instead we just feed the Y indirectly, because O and Y are supposed to basically be the same thing ideally. So if we just do this type of trick here, now you'll notice that this breaks up these long chains, because this is just part of our training set, and in fact we can disconnect this when we're doing sort of our inference. We can thus parallelize over just a single one of these computations. So we can split those up, and that's okay. So now this is great during training time. At test time, then you can't do this, because of course you don't actually have these YTs, but it's really just a trick that's useful during training time, and at test time actually you just connect it as we had in this image. So hopefully that makes sense. Teacher forcing is just an idea where we use the actual output as a proxy for the prediction at that time step when we're doing training. So yeah, it's important to note this difference between train and test time when doing teacher forcing, or when we're using this structure of neural networks. Okay, so the next thing we're going to talk about is optimization for RNNs. Now, optimization for RNNs is a little bit, it can be a little bit more challenging than for non-RNN neural networks, because there's a number of new challenges that come up, especially, you know, things like when we were talking about CNNs, we talked about vanishing and exploding gradients due to things like, and how, say, skip connections can somehow alleviate those. Well, we're similarly going to run into issues for RNNs, and we're going to see ways to get around those. So what I am not really going to talk about much is how we do back propagation here. All I'll really say is that we do back propagation through time. Which if you get back propagation, it's really nothing too different than what we've done before, in the sense that essentially you just sort of do the forward computation. That is, you do this computation through and you figure out what all these values are. And then what you can do once you've done the forward computation, you just do the computations backwards in terms of the derivatives and compute the gradients like that. So you essentially, if you just picture it unrolled like this, then you can yeah, then you can write pretty much the exact same type of gradient computation you would do on any sort of standard network which wasn't time-based. So yeah, that's not too bad. I'm not going to go into detail about that. But what is a challenge that arises here? Well, it's something similar, like I said, that we had with CNNs, where maybe long chains cause issues. And these issues, maybe I said in a previous lecture or not, I'm not sure, I'll just sort of say it again quickly. These are sometimes known as vanishing or exploding gradients. So what are vanishing or exploding gradients? Well, the idea when we're doing backpropagation, I'll just sort of say this in words to get the idea across. When we're doing backpropagation, what backpropagation is really a fancy way of saying apply the chain rule carefully. And you'll recall when you use the chain rule for differentiation, you're going to end up multiplying all the things in the chain together, maybe with a summation over different paths you can take. But it's basically going to be a big product of a lot of terms. Well, if you have a very long chain, say you have a lot of time steps, then you're going to be taking a product of many, many terms. So why is this bad? Well, this is bad because of sort of two reasons. Suppose you're taking a product of many, many terms, and those terms are all less than 1. Well, if you're taking a product of many terms which are all less than 1, then the product will end up being very small because, yeah, you take just because that's how products work. So yeah, that's what's known as a vanishing gradient. Essentially, when you have a bunch of derivatives which are each less than 1 and multiplying them together makes it so that your overall gradient is going to be very, very small. It doesn't even have to be that much smaller. Say you just have a bunch of things which you're multiplying, which are each, say, 0.99. If you multiply enough of them together, then this will eventually become too tiny if it's a long enough chain. Similarly, on the other hand, if you have something which is a bit bigger than 1, say 1.01 even, if you multiply enough of those together, then it'll grow sort of exponentially in the number of things you multiply. So therefore, that's what's known as an exploding gradient. So you can see that these types of issues where you have long chains and you're multiplying many things together, they can cause things to vanish or explode. And so these are some things that we have to deal with. And there's many different solutions. So some solutions. One way to do it is deal with it is to truncate the gradient chains. So what do I mean by truncate the gradient chains? Well, when you're doing backpropagation, perhaps instead of going all the way from the end of time to the beginning of time in sort of these gradient computations, instead what you can do is just do the gradient computation, and then after, say, like 10 steps or 15 steps or something like that, then you just stop, and whatever you have there, that's enough for your gradient. And you kind of do that for each path. So you kind of stop it. Yeah, so stop grad comps after tau steps. And this could be either a fixed tau, or it could be a random choice of tau if you want to add a little bit more stochasticity into the whole mix. That's one thing you can do. That would help with either vanishing or exploding gradients because it would prevent the exponent from getting too large. Another thing that you can do in the case of exploding gradients is what's known as gradient clipping. And what is gradient clipping? The idea is, it's a very intuitive idea. Imagine here's what your gradient looks like. It's very, very big. Well, what you do is just say it has to lie within some L2 ball in magnitude. So this is how big it is. This is how big your threshold is. And you just say, okay, we're not going to go with this. We're instead going to just go with something which is much basically clipped to the edge of this ball. So it points in the same direction, but the magnitude is attenuated. And one way to write this more mathematically is something like, given some gradient g, if the magnitude of g is greater than, say, v, where v is some threshold, And maybe this is the L2 norm. Generally we use the L2 norm if it's not specified, but yeah, this will be some threshold. Then what we're going to do is rescale G into, basically you take itself and then renormalize it. So that'll make it a unit norm vector in the same direction, but then you scale it up by V to make sure that it lies at this sort of clipping threshold. So GV times divided by the L2 norm of G. So recall that this is just going to be some number, so it's going to be scaling this number, not any sort of vector product. Okay, so that's another way to deal with exploding gradients. Now, the other way to do, the last thing I'm going to mention, is more than just a way to deal with exploding or vanishing gradients and like issues with optimization. These actually sort of, they're like tricks in terms of how to make the, not tricks, it's a rich line of research, so I feel like tricks is a bit dismissive, but this is a way to try to capture more expressive properties of the network, of this type of architecture, which can be useful. So I'm going to just mention something called gated recurrent units, which are sometimes called GRUs, or maybe some people call them GRUs, I don't know. And the idea is that we're going to take our previous computation, our previous architecture, which looked very simple, and just make it a little bit more fancy. So what we had before was something like this, where all we had here was some sort of just simple, one simple neuron. But in fact, I want to make it, each of these hidden states, I want to make them into a box. Like I want to make more fancy things happen within each state. So after we sort of implement GRUs, it's going to look something more like this. So I said before that there was no real difference between the circles and squares. Well, this time it's going to be a bit different because I'm just going to represent that there's something more interesting going on here. And then over here, this takes an input x sub t. And so these are going to be bigger boxes, and what goes on inside of these boxes, I guess to be consistent, let me just draw this as a circle because nothing changes about the x, that's just an input. But the idea is that this is going to be some box. So let's take a look inside this box here and what it looks like. So it's going to look something like this. There's going to be a few different neurons and different things we do with signals here. So this is going to be feeding in h sub t minus 1. So not too different from what we had here. And we're also going to have, as an output, we're going to have h sub t. And as another input, we're going to have the input x sub t. Now, the interesting thing is what is going to happen inside of this. So we're going to do, it's going to just, like what we would have before is just some sort of like neuron where we feed in both of these, and then it just gives us this. That would be what we had before. But we're going to do something a little bit fancier here, and I'm going to write sort of arcane looking boxes here. We're going to have something known as a reset gate, and something known as an update gate. And we'll finish filling in this diagram a little bit later, but the idea is the following. We're going to essentially try to write some logic here in terms of what we want to do with these various signals. So let's start off very simple. Let's pretend that we have some Booleans. So simplification, let me just note this down. I'm going to first get across the idea behind what's going on here, and then we'll sort of talk about more mathematically how it works. So our simplification is, suppose that we have some Booleans, so just reset and update our bools, so equal 0 or 1. That's all I mean. So the idea or the logic of this type of this cell, as we call it, this gated recurrent unit, is going to be something like the following. This is kind of what we want to do. Of course, like, we can't write if statements using neural networks this easily, so we're going to see how to translate into neural networks, but we're kind of going to want to do the following. So if update equals 1, then what we would do if update equals 1, then it's kind of backwards, I guess. We just leave it to be the old thing. Yeah, so okay, if update is 1, then we just say ht is going to be ht minus 1. So kind of just skip this input and ignore it entirely. Now what we do in the other case, if it's going to be 0, then what we do here is we look at the reset gate. So what do we do if reset equals 1? Then we let h sub t be equal to, say, tan h of u x sub t plus w h sub t minus 1 plus b. So this here is actually should be very familiar to you. This is just a standard update. Right, so this is just a standard RNN update. It's just going back to the basics, what we had here. And in the other case, like the else case, remember this is when both update and reset are equal to 0. Then what we do is we set ht to be equal to tan h u sub xt plus b. So this just says drop the old state. Or just basically, yeah, this is just an MLP of the current input. Okay, so yeah, we can see that under these sort of somewhat bizarre, I agree that this is a bit bizarre what we're doing here. We define some Booleans and somehow we apply them to make sure our output is some certain function of the input. But bear with me, we'll try to see how we actually implement something like this. We basically have 3 types of operations we can do. The operations that we can do are basically either use the old state, that is, ignore the input. Another thing we can do is we can go the other way, where we drop the old state and we use only the input. So in this case, we use only the input and drop the old state. And the last case is where we just sort of ignore it and just treat it like a standard RNN. So this can be, this shows how flexible this can be, because, for example, if there were, say, a long-term dependency, so we want to keep the beginning of the input sequence for a long time. For example, say we start a sentence with he or she, and we want to propagate that to be able to understand whether the target is a male or a female, or uses he or she pronouns. Then we would want to maybe use update as our, we'd want to have update on in terms of our states, because say we're just trying to predict that, then we need to keep it propagated. Of course, this may be a little bit contrived, but you can see how it might come in handy sometimes. That's one thing. Another thing that you want to do is maybe just like not have a memory. We want to perhaps just ignore the past states and just do each thing independently and not get confused with the past. And we can do that other extreme here. And we still want to maintain all the expressive power that we had before with an RNN, and so we can just do the middle. So you can see that this is kind of some helpful logic in terms of encoding what we want the sort of function to do. Now, what should I note about this? Let me comment a bit more about this, like vanishing exploding gradients. Sometimes if you're doing the computations such that you skip states, for example, yeah, maybe you just drop the old state and then go to the MLP type thing, then that would essentially it would require fewer gradient computations. Similarly, if you just skipped, it would basically truncate the chain there in effect. Similarly, if you just use the update, then it would skip the input, and that would be one less gradient computation you would have to do in terms of with respect to the input parameters. So the idea is that by using these types of logics here, if we could use them, then we would be able to do fewer gradient computations and not have as long chains. So that is handy. So now, okay, let me do away with this sort of like lie I've told you, the simplification that we did. In fact, it's very hard to do this sort of making things into either 0 or 1s. But in fact, what we can do is we can make sure that things are between 0 and 1. So we're going to have kind of soft if statements. We're going to have things be linear combinations of these different options. And yeah, that's one thing. And the other thing is, rather than having just if statements, we're kind of going to try to apply this. These kind of apply to the whole vector at once. But instead, we are going to apply them kind of coordinate-wise, in the sense that maybe different coordinates, different parameters could be updated, some could be reset, and so on. Okay, so let's talk a bit more. I've given you a bunch of intuition and stuff now, but let's be a little bit more mathematical here. So the idea is we are going to define some signals, RT and ZT, which are going to be our, this is going to be our reset, and this is going to be our update. Signals. So what we have here is, say, it's going to be a sigmoid of, these are just going to be combinations of our inputs as we've kind of got them before. It's very similar. Say U sup R T, W sup R, HT minus 1 plus B sup R. So note that I'm defining some new parameters here. These new parameters are specific to the reset gate, which connects the input at a time to the reset gate. They connect to the last hidden state to the reset gate and a new bias parameter for it. So they're specific to the reset gate, but they're shared amongst all time periods. So similar parameter sharing. And also, we're going to do something like this. U sup Z xt plus W sup Z A sup T minus 1 plus B sup Z. So, okay, so essentially we've done the typical neural network neuron thing where we just connect things up and see what it gives us. So let's sort of draw what this might look like pictorially. So we've essentially connected this here, and we've connected this here, and we've also connected this here and this here. That's kind of how that goes. This is sort of in encoding here, except with some additional multiplications and stuff written in, but I'm just going to draw it pictorially just to keep this from getting too complicated. Okay, so now that we've got these reset, oh yeah, let me talk a bit more about these. These are both, because we did sigmoid, these are both going to be vectors, which are in 0, 1 coordinate-wise. And these are going to be the same dimension as the hidden vector h sub t. And the reason for this is because they're going to essentially act like masks. Like I said, we're going to be trying to apply these update things parameter coordinate by coordinate. So we're going to somehow use that. So let's see. So, okay, these are our signals first. Now the next thing we're going to do, we're just going to define 2 more signals. So we're going to define this, which is going to be our candidate thing, our candidate hidden state. Okay, something like this, and I've done this unfamiliar looking operation here, but this is the coordinate-wise product. And the idea is we're just going to multiply each coordinate of h sub t by either some value that's within the interval 0 to 1. Now let's just take a look at what happens if we're at the extremes, just to see how this matches up with what I told you before. Suppose r sub t is all zeros. That is, we just totally zero out this vector h sub t. That corresponds to reset being 0. And it's essentially this case. So you can see if you set r to be all zeros, then this term disappears, and it just becomes ux t plus b, which is exactly what we have here. That's one extreme. On the other hand, if we have r sub t equal to the all ones vector, then it'll just preserve it and be a standard RNN, and it'll give us exactly what we have here. So this will just be an all ones vector, so it'll just replace it with h sub t minus 1, and so on. So yeah, this essentially, this is our what we call our candidate. Because we don't output it yet. But you can see how, hopefully, how if we enter this if statement, then it's essentially equivalent to what we would output. But the last step that we do is essentially choosing what h sub t is going to be. And this is not too complicated. It's just going to be this times this. So you can see what we're doing here is we're kind of doing an if statement between either outputting the past hidden state versus the candidate hidden state. So you can see that if z sub t is equal to all ones, this corresponds to just outputting this h sub t minus 1, which is exactly what we had if update equals 1. And on the other hand, if zt equals all zeros, then we would output this candidate hidden state. That essentially falls into this else statement here. And then we can see that this is exactly what we had already reasoned about there. So yeah, this was perhaps a little bit odd, but we essentially showed how the goal is to try to emulate these if statements that we had here on a coordinate-wide basis. But of course, because these can be anywhere between 0 and 1, it can also be linear combinations of these behaviors as well. And yeah, this turns out to be pretty effective, these GRUs. Yeah, and I guess let me maybe state something that's implicit here, but just to make sure it really gets home here. The idea is that the really wonderful and amazing thing about deep learning and machine learning is that all of these things here are really just trainable parameters. We never specifically hard-coded, okay, we're going to do an update, we're going to do a reset, we're going to do these things. These are just sort of intuition behind what we believe or suspect could be going on. In reality, what we do is we just plug in these parameters here, which kind of tell it, which kind of just encode it into some parameters and say, okay, figure out whatever parameters are supposed to be here, learn it using gradient descent, and then it can somehow figure out these complex functionalities, which we just sort of wrote simply as if here, and it just chooses the ones which work best given our data. So yeah, despite the fact that we define some sort of very complex logic here, it still is able to it's still able to figure things out, and I consider that somewhat miraculous. Yeah, machine learning is awesome. What can I say? Let me finish off this diagram, I guess, just because I started it and might as well finish it. So the idea is what we've got so far is that we define these R and Z things, which just take in the inputs. And the idea is that we're going to get some signal here, which basically comes out of the reset gate, which will be H tilde of t minus 1. And then based on the logic that goes on inside the update gate, then we essentially generate whatever h sub t is. So I didn't write this out in full, like in the sense I didn't include all this logic here, but this is just a little caricature of how the information and the signals flow through one of these little cells. Good. So that is the gated recurrent unit, the GRU. This isn't the only type of sort of cell or like gated unit that appears. There's actually a much older one called the long short term memory, often called just the LSTM. This is actually, surprisingly, this is a much older type of model. It came from long before, maybe like 20 years earlier. But it's kind of very similar ideas, except it's more complicated. Like this one has 4 gates. The LSTM has, GRUs have 2 gates, whereas LSTMs have 4 gates, and they have 2 outputs. They have not only like a state, they also have something else they call, I think, a memory. But yeah, these are more details than we're going to get into during this lecture, just because it would be kind of going through a bigger if statement for you. So like you can do that on your own time. But these are rather important. You should, I'd hope if you're interested in this area that you'd look them up and try to understand them a bit more using this guidance that I've given you for GRUs as sort of a template on how things kind of work. Yeah, it's basically just trying to use deep learning to encode types of logics, like how to preserve and whether to erase signals and stuff like that. But yeah, just too many details that I'd like to go into here. Cool. So let's just close up by just talking about a few final notes about RNNs. So one thing that you should know about is bidirectional RNNs. And these are useful because of the fact that most of the problems we've talked about so far are kind of very naturally things that you would go in one direction. For example, if you want to predict the next word, well, it's predicted based on previous words. You can't really necessarily predict the next word based on future words. So it doesn't really make sense to do, it makes sense to only go forward in time there. But let's suppose you were looking at a sentence. Sometimes looking at a sentence, you might need to look both forward and backward at the same time. So let me be a bit more concrete here. Let's say, as an example, I went to the bank. So what does it mean when I say I went to the bank? What is the bank here? Well, you might have some guesses. There's banks here. You could go to maybe there's different options is the point I'm trying to get at here. This is ambiguous. So there's 2 different options that come to mind immediately for me. So one is I went to the bank up the river. So it's a river bank that it's referring to. And the other one is I went to the bank to withdraw cash. And this is a bank for money. So you can see that based on the suffix of the sentence, it tells you what exactly this bank is. So this is kind of a problem known as named entity recognition sometimes. But yeah, like there's some ambiguity in what's going on here, and you really need to see both the forward and backward parts of the sentence in order to understand what it's referring to. So let's see what is the this is a kind of picture of what the architecture might look like, just to save some drawing time. Use this. And yeah, this is like an RNN with essentially just forward and backward parts. So let's see what's going on here. Let's first of all just X out this layer right here. Let's just pretend that's not there. If you do that, well, this is just an RNN exactly like we've seen before. You can see that it computes this hidden layer. This hidden layer goes forward in time, and then we have some outputs, goes into a loss function, and so on. So now the difference is we have this hidden layers going forward, and as well we have these hidden states that also go backwards in time. You can see now we have both forwards and backwards, so that's why it's called bidirectional. And essentially you just do it the same as before. You just have the edges going in the opposite direction, but besides that it's pretty much the same. And you can see how now when you're doing the prediction at say time t, then you're going to have, when you're doing the prediction at time t, you have both things from the past as well as so this has a like things from the past, or yeah, as well as things from the future. So somehow it depends on all inputs at once, which can be handy for certain tasks, like such as this type of problem here. It wouldn't be appropriate for other things like when we're doing, say, next word prediction, because of course you can't use information from later layers or later words when we're doing predictions of earlier words, because that would be too easy. You could just predict the next word based on what the next word is going to be. Okay, so that's one thing you should know of. The next thing I'll mention is how to make RNNs deeper. Well, the same way we always do it, just you add more layers. So let me just draw a caricature of what is going on. So like I'll just draw it simply like this. So these are going to be our inputs, and so this would be x1, x2, x3. I'm just not going to write it there because it would be maybe tedious. Just want to keep it concise. Then we'd have here our hidden layer, h, and these would feed forward through time like this. Now, if this was just a non deep RNN, then we would just have something like maybe like this, y hat, where we would predict each of these like this. And that would be the end of the story. That's just a standard RNN. Well, how do we make this deep? The picture is very suggestive here. So all you really have to do to make this deeper is just add additional layers in here. And yeah, in comparison to other types of networks, maybe you wouldn't want to make this quite as deep as, say, like any of the deep CNNs we saw before. But yeah, you can just add more layers like this, which are just hidden layers, just in the same way as carrying hidden states, just the exact same way that H is. And yeah, nothing too special. You just do all the computations as before. Cool. And the very last thing I will mention is the encoder-decoder type of architecture. And this is an important style of architecture. It's useful even in non-RNN settings, in the sense that it has a very conceptually like simple way of understanding what is going on. Here is a picture, again, from this very helpful deep learning book. So what you can see here is the idea is that we split the computation that we want to do into two parts. One part will be the encoder, and then the other part will be the decoder. And the idea is that what we're going to do is we're going to start by taking our input of what our sequence is, say our points x1 through xn, which may be variable length. They're going to produce some sort of C here, and this is known as the context, or it's called a context sometimes. And then at this point, once we have this context C, then we can just in fact do away with this encoder entirely. Then we feed this context into a decoder, and you can see how this is used at sort of every sequence in the network. So it can be fed in and determine the Y's sequence. It can also be fed into these hidden states here, and the hidden states can be determined by previous things that we're going to output, and so on. But the point is that it's a really decomposition of the network into two different parts of an encoder and a decoder, which is very conceptually useful at many points. Let me give you one example where this is sort of very common, which is machine translation. And the idea is the following, where first you would feed in your sentence as these x's right here, and that's whatever sentence you want to translate. And the idea conceptually is what it would do is it would spit out something C. And the idea here is going to be that C is some sort of language agnostic representation of that input sentence. So suppose you put in an English sentence, well, now it'll just be some context C. And the really cool thing is that at this point, given some context like that, then if you sort of train it in an appropriate way, then maybe you could feed it into different types of decoders. So for example, you could connect it to a French decoder and it would give you that French language, that sentence translate into French. Or you could you could instead put in a Chinese decoder and it would give you the same context, the same sentence translated into Chinese. So yeah, it's kind of neat that we can, you could potentially separate these two tasks into different points, into different neural networks of their own. So yeah, that's all we want to talk about today. So these RNNs are a very powerful type of idea. They're very useful for sequence data, which is kind of ubiquitous and comes up all the time. Yeah, and they're a good thing to know. I'll say that in terms of the most modern things used for language models, there's actually something different which is used now. It seems that recently things called attention mechanisms are somehow more powerful and get around some of the downsides that we've talked about with RNNs, including, say, long lengths of dependencies and stuff like that. So yeah, hopefully we'll get to that in another lecture, but nonetheless, RNNs are very important and they are a thing you should definitely know.